Okay, well, we'll get started. Do you shut that one off, Reiner? Where is it?
That's all.
Okay, we'll get started. The first two presentations this morning, and I gotta get my schedule in front of me. John, G4SWX is going to speak to us on beyond DJ9BV, and I'll read you a little bit of his background. John has been licensed for 55 years, catching the EME bug after being inspired by a presentation by Peter, G3LKF, in the mid-1970s. Finally getting on EME from his own station in 1984, John's interest has always been in 144 EME, having worked over 2,000 initials in 172 DXCC countries. John has always been a keen home constructor and has also designed and built his own EME array. What is slightly novel about his station is that in 2011 it has been comprehensively remote controlled over his own IP network. John has been the RSGB VHF manager for the past 14 years, dealing with both UK and international radio regulators and representing the RSGB at IARU. Now retired, John worked for 40 years in telecommunications and completed his career as a distinguished engineer dealing with critical national infrastructure issues with the UK, Canadian, and US government. Please welcome John.
Good morning. Oh, good. I'm 5 and 9. One thing to say about me and working career is I once had to accompany the chairman of my company into an event at one of the intel agencies as his resident expert. And he said, "John, it says distinguished engineer in the directory, but what do you really do?" And I said, "No, I am a cynical engineer. I don't believe what people tell me. I question it until I can trust it." And that's actually why some of this happened. My colleague, John Sager, who wrote most of the software, used to be my head of software security for 25 years. And will break anything, even if it's embedded in a chip with no terminals to talk to it. And he has also been a drinking mate of mine for 45 years. And we discussed this last autumn in a pub. And that's why we came to this work. Very much, it's very sad. We started with the work of Rainer, DJ9BV, who very sadly died in May 2008. Rainer was a great inspiration to help me technically on EME in the 1980s and 1990s. We corresponded a lot. What did he do in 1987? He published an approximation of antenna temperatures, which was a simulation of antenna array properties. He worked really hard with a Sun 3-160 workstation and NEC2 simulations. By comparison, the thing that sits on my desktop at home, or perhaps even the laptop, has got 10,000 times the computing power that Rainer had in 1987. So it took him over 100 minutes for 3 degree steps of the synthesis in theta and phi for a 4 Yagi array for 70 cents. It takes me less than 10 seconds, including a software wrapper in 4NEC2 that does all the precursors and and everything else. I actually like 4NEC2 as a wrapper around NEC4 because all of my antenna simulations are written as algebraic equations. So I don't use conventional amateur type methodology. Everything is in algebra, and therefore as it's algebra, everything can be changed and everything can be tweaked as a variable. That allows me to do the most incredibly fast things in optimizing arrays. And just as an aside, we're talking about my I started this because with my 2 meter EME array that I published at EME2022 in Prague, when I got to using it heavily, I discovered I was getting better Y-factor calculations than VK3UM's programs predict. VK3UM used the approximations produced by YU1AW, and those made assumptions about antenna stacking and noise temperature. So that didn't fit, and then on top of that, a certain German station that publishes in Dubus criticised my aerials, so that couldn't stand. So, in 1987, DJ9BV did a very simple synthesis on his neck file. He'd said, sky is 15 Kelvin for 70 cents, ground is 290 Kelvin. He'll take a slice, which is the front pointing part of the antenna, rear part of the antenna, and then he'll do a summation based on the integrations from his NEC file. Relatively simple, and it works moderately well for 70 cents. But it works on 432 megahertz because T-Sky is much, much smaller than T-ground. He had 15 Kelvin, nearly 300 Kelvin for the ground temperature. So that the rear end clutter from an array was equivalent-ish to the front lobe plus the first order side lobes. I'm not happy that the E7BQH took that to 144 because T-Sky is of the order of T-ground, in other words 200K and 290K, and the only way you could get it to work was E7BQH made the ground 1000 Kelvin, and we'll deal with that in a minute. It's irrelevant on 50 megahertz where T-Sky is many, many times T-ground, even at the quietest point of the sky. And some have played with numbers of T-Sky and T-ground to produce tables. Some of it comes down to the choice of the noise temperature. In the introduction it said, I'm the VHF manager for the Radio Society of Great Britain. I deal with the radio regulator in combat sometimes about what is acceptable interference, what is excessive interference, how do we deal with shared amateur bands and the signal strength, what should it be compared with the ITU noise floor. There's a set of ITU tables, they've been updated about 10 years ago. Our regulator doesn't actually agree all the dots are down to his measurements. However, ITU P372 standard is based on a statistical noise model around a grounded monopole. That has a first Fresnel zone, which is circular and fairly close to the antenna. Any form of amateur antenna, unless you use an FM vertical on a car or home, is totally different. A Yagi array has totally different first Fresnel zones. Each lobe in a Yagi array has a different Fresnel zone when it sees the ground. You cannot take a massive number that was suitable for a grounded monopole and sits in the standards and works moderately well, except in some cases for mobile radio coverage, etc. I believe it's fundamentally engineeringly wrong to try and put that into DJ9BV's equations, which is why I think so many people are wrong. You can recalculate it for the main lobe at a given height. It's just as complicated to calculate it for an antenna pattern because height matters, because where your first Fresnel zone is and the angle at which the radiation hits the ground or is reflected from the ground is totally different. The synthesis of this can be done, but it's more difficult than what I'm going to show today. So I have chosen 290K as the most appropriate choice. It might be 300K, it might be 273 or whatever. doesn't matter, it's around about there. Okay. We started off and we looked at the stuff by OM6AA that was presented in Jubas, and I think it might have been an EME conference, but not when I was going. He used Microwave Studio and FICO antenna data, and with people from the University of Prague, they wrote a very complicated, overly heavy, because it had to be programmed to calculate antenna noise. And they used a table of environmental noise for the sky temperature. It's useful for dishes, but I don't have CST Microwave Studio and FICO won't cope with the sort of arrays I'm designing. So, good start, we looked at it, we looked at the maths. Okay, what do we do for our sky temperature? Almost everybody uses Haslam's published data, 1982, 408 megahertz all sky survey. It's the basis of most subsequent VHF, UHF data sets. At this point, Michael W9IP flagged to me the possibility of using LFMAP, which was published in about 2003 by the US Navy labs. LFMAP is a correlation function between 22 meg sky data and 408 meg sky data. We weren't quite happy with it when we tried to do antenna noise mapping because it had greater extremes, and I think that's down to the correlation in the data. So, we started again. We did a complete scientific research job on the literature. I started my life, and my colleague John started his life as research engineers, although we ended up as information security hooligans. In 2003, published by Platina et al., they put a paper up where they'd removed the instrumental artifacts from the original Haslam data. That's important because there were a lot of artifacts in it. This was then slightly modified by Remaz Eliz in 2015. It's the chosen data set we chose for originating this paper. It was the reprocessing of the Haslam data with modern algorithms, and it's available for download on NASA's Lambda server. Now, there are two extra features. When you're looking at scaling 408 megahertz data, noise data, you have to do extragalactic noise corrections. You have to take it away at 408, and then you have to add it back in after you've done some manipulations at 144 or 432. The next thing is there is no simple spectral index, so it's not e to the minus 2.6. It's something like that, and it changes with frequency, and so the spectral index is very, very hard to compute. We took a very recent paper in 2025 for the recent spectral index figures. So that's the background of looking at the research for our noise data set. Before I go into the actual hardware of the things, I need to talk a bit about map projections. Everybody is familiar with equirectangular projection. Invented by Marinus of Tyre around about AD 100. And that's the sort of thing that you get from VK3UM, which is, again, the same projection. It's very familiar, everybody knows how to work with it, but it has significant distortion if you want to use it for computing data. And it has very, very inefficient data usage. And we're talking of huge data sets for the 408 meg sky data. So that's what everybody's used to. We're from the EME community. So we're accustomed to the Molwind projection, which is an equal area pseudo-cylindrical map projection. And it's generally used for maps of the world or the celestial sphere. It's about 220 years old, and it trades the accuracy of angle and shape for the accuracy of the proportions in area, so that where the proportions in area are needed, such as maps depicting global distributions, it's more accurate than the angle and shape. And this is a map that we're all familiar with. It's taken on the galactic plane this time, and it's the 408 megahertz map as we downloaded the data set from NASA's server, which was refined in 2015, this particular one. So looking at 408, we see a variation between 10K and 400K, and that is centered on the galactic plane. Now we get into the complicated bit. There is a moderately recent projection called HEALPIX. And HEALPIX is an acronym for Hierarchical Equal Area Isolatitude Pixelation of a Two-Sphere. Now that sounds overly complicated, but it's actually an algorithm for the pixelation of a two-sphere. It was devised in 1997 by Gorski at the Theoretical Physics Center in Copenhagen. So you can look at the map of the world, which is generally like an orange. It's basically sliced up and pulled apart. So that gives you an idea of what the world looks like in a HEALPIX prediction. There's very good reasons why we used HEALPIX, and we'll get onto that in a minute, because what we needed to do was get our data set into a projection where we could use simpler mathematics and not have millions of CPU cycle times to calculate anything. Okay, so we produced a set of sky temperature maps. We used the HEALPIX data format because that is what is used by astronomers today, and that is what is used by radio astronomers today. We used the reference epoch of J2000. That is the relationship of the galaxy to the solar system. It changes a little bit year by year, but it's only minutes of time of data in a year. We thought about trying to update it, but actually the change in accuracy is not very large. We use the Ramalah's sky map in HEALPIX data form. So if you imagine the data set that we've got is equal area on a sphere. Now if you think that you want to try and map your antenna pattern into the galaxy Skynoise, having equal area on a sphere for that number makes it very, very high in resolution. There's no rounding errors. However, we then took the data set, which was huge. Even in this format, it's 3 million data points in galactic coordinates, which is very, very big. The sort of maps you see in the amateur sphere are only 200 or 300 points in some other coordinate system. So we took the 3 million data points, we reduced that to 197 in equatorial coordinates. And the reason for that being is that we didn't think that we needed better than 1 degree resolution on our integration of pointing an antenna at the sky. We could have done it for 0.1 degrees, but the computing gets to be 2 orders of magnitude greater. Now to explain the temperature. I talked about the scaling. So at 144, it was the coefficient at 408 minus the galactic noise at 408 plus the galactic noise at 144. It actually, the constant ends up at 2.56, which is close to the 2.6 we recognise. And to scale from 408 to 432 megahertz, that was 2.617. So from that, with our extra galactic noise corrections and the spectral index for doing the scaling, we felt it got to be a highly accurate map. So we produced map files for both 144 and 432 to start with, but we could do it anywhere between 50. I think at 1296, the extra galactic corrections actually show up the error sets in the 408 meg data. I'm sort of uneasy. I'd rather take a different sky map done at a different frequency as part of the scaling. Well, we know what this is. What we have done is we have changed to solar system equatorial coordinates for the projection. A 144 meg sky map looks exactly what you'd expect it to look at that. At this resolution, it's not any different from anything else you've ever seen. However, we used heel picks. Now, I apologise for this. The viewer that I have, I've had terrible jobs with heel picks viewers. This one is thanks to Michael W9BV. However, it overlaps. So that bit there is really into that bit there, and you have to slice it at 180 degrees. This colour scheme is odd. Both the guys that reviewed it for me said, why is it very odd? And I said, because the scale is extreme. It starts at 150 Kelvin here, and I've stopped it at 2,500 degrees Kelvin. As you can see from the sky map, is extreme. There's 170,000 data points on the R-sphere. So on 2 meters, quietest sky is 170 Kelvin. And I can tell you that with a fair level of assurance. And the noisiest sky is about 6,000 Kelvin. Let's go a little bit deeper into it. We did a lot with the sky data. We did a lot of hill climbing algorithms with a blob that we thought was equivalent in size for the projection of a large 4-Yagi system. And so we did hill climbing to find the quietest point in the sky. And the quietest point in the sky is about 170 Kelvin at 144. It's 142 RA, which is 9.5 degrees for those that work in old units, and plus 30 declination. I'd had lots of debates whether it was there, or there, or there, or there, from what I can measure on my own station. But having done the hill climbing on the data set, I believe it, and when I point there, that's definitely correct. So we've set what we decided was quiet sky by hill climbing against our sky data set. And we think that that is highly reliable. So where is it? Lots of people say, oh, beam at Leo. Well, Leo is generally taken to be around M65, M66 stars there. Where we are is just out of the main part of the Leo constellation below me at Leo Minor. And that actually corresponds fairly well with the data sets. So, and I'm not going to go into this particular star projection because it's even worse than the ones I've discussed earlier. Well, 432 in mind projection looks exactly like 144. The difference is it varies between 10 Kelvin and 400 Kelvin. You wouldn't expect it to look any different, except the numbers to be different because of the different scaling factor and the different constants. And if you look at the Heel-Pix sky map, and remember the triangles on each end are an artifact of the viewer that I used because it goes beyond 180 degrees, which is there and there. It looks like the 144 megahertz one. It has the same level of granularity, and look, Quattro sky is about 11 Kelvin, Noise's sky is 1200 Kelvin. 432 megahertz quiet sky, when we did our hill climbing with our spot for a perfect antenna, which was typical, we found obviously, because something would have been very wrong if it hadn't been that with the hill climbing on the data set, that the quietest point in the sky was the same place, 142 RA or 9.5 degrees plus 30 declination. And the quietest spot in the sky for this comes out at about 11 Kelvin. Okay. This is down to my friend John G809H. After many beers in the pub, after going through piles of scientific papers in the pub over what was the right data set to use for the Skynoise, we calculated the antenna noise temperature. John wrote it in Python because although there are all sorts of things available, a lot of the astronomers have written algorithms in Python to do this sort of job. So we used numpty for the array matrix arithmetic, Astropy Heel-Pix for the interpolation, which is a fairly well recognized algorithm for astronomy interpolation. We took the NEC output file. I use NEC4. We'll discuss in the second part the ins and outs a little bit, but you have the model vectors of theta and phi for your radiation pattern from your antenna. We then calculate RA and declination for each of these 1 degree steps from our QTH, longitude, latitude, antenna azimuth, elevation, and time. And then we interpolate the antenna temperature from the sky data set with the RA and declination arrays. We read the gain from the NEC data, and then we integrate it over 360 degrees azimuth and 180 degrees elevation. That's minus 90 to plus 90. The coordinate system is quite difficult to get absolutely right. The integration looks like every other integration you've ever seen for antenna noise. At 359, because we don't actually repeat the data points at naught, because if you did, you get an error. Temperature for the vectors set below the horizon, in other words, pointing anywhere at the ground, have been set for 290 Kelvin. It's live, it's available, anybody can download it. It's on pypi.org, Project Skynoise. And yesterday, John has put the source code on another public domain site for doing this work. So, giving a little indication, I can calculate now the antenna noise temperature for my array that I have modelled whilst beaming at quiet sky. That was the nice and easy bit. And that produced some remarkable numbers, as you will see in the second part. I can do it whilst beaming at the moon. All I would say is I don't include the moon noise and don't include the sun position. Having had a lot of experience of it, the approximations for sun noise at 144 are nearly all wrong. I have never, ever, since I put this array up, managed to measure Skynoise that any of the prediction programs come up. I always measure more. Sun noise, yes. I measure a lot more sun noise. Because the relationship with frequency for sun noise takes a very awful turn and curve below 400 megahertz, and it's really difficult. But don't worry about it. So I've taken a near perfect field. We don't bother below 10 degrees because below 10 degrees ground reflections start to get highly, highly complex. We don't include ground reflections, and I'll deal a little bit with that in the next part. We don't include moon noise. Moon noise is probably just about noticeable on 432. The moon subtends about half a degree. Your antenna, if you have a good long Yagi, I mean greater than, I don't know, 5 lambda Yagis, you probably have something like a 12-degree spot. So in an area, the moon, which is only subtending half a degree, is a relatively small part of that area. So the moon noise doesn't particularly matter for 144 and 32. Then I started using it in ADA in about January. It's more revealing of Yagi antenna array performance than any existing method. I have the greatest respect for what Rainer DJ9BV did in 1987. He did wonders with the computing that he had. The thing is that nobody since then has tried to do the job properly with modern computing. He couldn't do what we're doing. 3 million data sets here, so many million data sets there, and only 8 seconds on a processor versus 3 hours. It's crazy. So, what can you do with this toy? This is a taster for the next part. This is my array. Using DL6W calculated stacking on 144, and this starts on the 17th of June, in other words later on in this month. This gives the expected temperature calculated for pointing at the moon with my array. So it tells me what I would expect. Unlike everything else, like Joe Taylor's WSJT variants, where he takes the sky in 15-degree sectors and says that's what the sky temperature is. This is what the sky temperature that my array sees. So it's probably seeing something quite nasty in the side lobes at that point. That bit going down is moonrise to high elevation, and this bit going up is towards moonset. So the sky noise is changing, but the amount of ground noise and the aerials are changing too. As you would gather from this, I can see at any point in time what my antenna temperature should be, and I can go and run the program up and point at another point in the sky. What I will say is that although it works well for Sagittarius A when you could see it, Y factors work well for that. The trouble, certainly on 144 Cassiopeia A, is that Cassiopeia A is almost a point source. And the smoothing algorithms that we have used to produce our map make it very difficult to do very accurate Y-factor correlations with it, with Cas-A. So we can do this. It's simply manipulating the software. So, in the first part of my presentation, what have we done? We've taken an NEC model output file and computed for 1 degree steps. We computed the integration of the pattern against new sky temperature maps for 144 and 432. I can tell you what it will be for 220 just by interpolation of the two, but it's only a few errors to produce a new sky map for 220 or 50 megahertz. We honestly didn't bother for 50 megahertz because it's just too bloody noisy. We could produce a calculated antenna temperature. You choose the coordinates, we can do it. I've made a proposal for where it should be in the sky. I realise that part of the sky is not terribly visible in the southern hemisphere. It's very suitable for the northern hemisphere. And there are other bits and pieces about comparing one station with another, and that's beyond the subject of this talk. It's probably in the masterclass that will require 3 or 4 beers to me before I open up the PC. And it can be further applied for moon position using moon passes. I know what my antenna temperature is because I've taken great pains to measure it. I know that on 144, my whole system temperature is about 244 Kelvin, and I can prove it. And that's many, many years, I mean, it's 40 years of EME and some serious computing and engineering of different presentations to go into it. So at which point, this is the uncomplicated bit. I'm looking for questions on part one. The software is available. Skynoise. The graphical user interface is a bit clunky. It's written in Python. Very lucky, I did all of my work to produce the second presentation with a command line interface. It's to do with actually trying to take the ideas of Skynoise and how we design antennas and calculate antennas into the 21st century. And that is why I entitled it Beyond DJ9BV. Questions on part one? Michael?
I think it might be useful for you to speak briefly about the connection between the temperature of the sky and the temperature of the antenna. What is, how are they linked, and how does one speak to the other?
The way that I've done all of my calculations is I take the feeders to be part of the system. So your feeder relays preamplifier and that I take as receiver noise temperature. I've separated out antenna noise temperature. The antenna noise temperature takes about 5 parts. Originally, about a year and a half, 2 years ago, I tried to take the DJ9BV model, which is one temperature for the sky, one temperature for the ground, and break out the 30-degree elevation piece, because within 30 degrees beaming, you've got all 4 first-order side lobes. And the first-order side lobes are the bits that pick up sometimes perhaps half the amount of noise that the main lobe does. Then you've got all of the funny back-end clutter, multiple reflections and all the rest of it, and that's another component. So it varies between which band you're on, which is the biggest contribution of to the noise. I'll tell you that on 1296, you virtually see no sky noise with a Yagi array, almost none. My recommendation, which will be in the same thing, is Yagi's on 1296, please use a dish, because you'll be deaf. On 432, the situation is incredibly complicated, as I will show in part 2. On 144, it turned out to be relatively simple. And when we extrapolated it to 50 megahertz, I would just say I would follow Lance W7GJ's recommendation, which is gain matters. Forget everything else. You want as much gain and as much power as you can get on 50 megs. And that's it. Other questions?
The order doesn't correct.
That one?
Yeah.
I'll check it later on, right?
Yeah.
I will check it because I can show you on the lap. I can also put the